the task is just implementing BFS as is, you know, in the simplest version. You are given the graph, the edges don't have any weights, and your objective is to go from start node to any given destination node. The basic level of understanding is going to be enough to solve the problem. However, if the problem is a little more complicated, let's say the edges have weights, or you are looking for the second shortest path to the destination, like if it has this type of modifications, if your level of understanding is at the surface level, it is going to be hard to do that. So if you find yourself with an algorithm, hey, I know this algorithm, but when the questions come from this algorithm, I am not able to solve them all the time. Or most of the time I'm having a struggle. This means most probably you are at the surface level of understanding of this algorithm. And to be able to perform well and be above consistently over the bar in the top tech companies' interviews, we need deep level of understanding of all the basic algorithms that we are covering. And for that reason, it's really important for you to understand, if you are not very good with the basics, first we're going to start from the basics. So from time to time in the contests, we have questions that are not just solved by the basics. If you see questions in the yesterday's contest, majority of them were that way, right? So in terms of topics, we have covered all the topics. Like none of the questions were solved by a technique that we didn't see before, right? I mean, everybody has been part of this. Maybe we haven't seen it in this camp, but we have seen it before. And indeed, I think all the problems were coming from the topics that we had covered during this camp as well, right? Still, we see that they can be challenging. And the reason is, if we don't have deep level of understanding of the logic, the necessary modifications are going to be hard to see. For that reason, I highly recommend everybody to understand the logic behind. So it shouldn't be what BFS is, but it should be why we do this at the beginning of it. And why do we do this after? Why is it working? We should understand all these things. And if you don't understand these things at the moment, this is very normal, guys. Because we weren't consistent on this, we weren't practicing on these problems for a very long time. However, let's understand this. This is the level of understanding we need to reach. And everybody in this class has the capacity to understand. Team, I had personal time with all of you until this point. Maybe with some of you guys not much. Maybe I would say 2-3 people in the class still that I don't feel super close with. And even those people, you can look at your previous results. Just imagine the toughest problems that you were able to solve until this point. It actually proves that you have the capacity. Like if we have seen a clear outlier in the class, we would talk with that person before. And that's not the case. If you are still here with this group after this long time, it means you have what it takes in terms of potential. At the same time, we need to do the hard work, we need to do the focused practice so that we are going to get to this deep level of understanding of these algorithms. Okay? So that's why in today's session, I will focus more on the logic part. And moving forward, when we are covering these algorithms, let's try to understand the logic. Because if we don't understand why every single thing we are doing in this algorithm is done, then it means the logic is not going to be there and the modifications are going to be hard. But once we get it, then on top of that, if we put the practice, it's going to be a lot easier. And as we know, graph traversal algorithms, I would say maybe 30 to 40% of the interview problems come from graph traversal algorithms. Like this includes depth first search, breadth first search, topological sort, sometimes shortest path, and I would say also maybe union find. We are going to be also covering that. And if we look at all these topics as graph traversal algorithms, I would say 40% wouldn't be an exaggeration in the ratio of these problems coming in the interviews. For that reason, these are very important topics, very essential topics. And let's try to get to the root cause of every single detail of it. And we can do that, guys. There is nothing like rocket science in this. Nothing is super complex or complicated. So we all can understand the logic. And if you didn't get the logic yet, that's fine. That's fine. We are going to do practice. Feel free to ask other team members. Feel free to talk to your mentor. Feel free to talk to me. And hopefully, in time, we are going to get there all together. Thank you very much. Now, let's get started. So, breadth first search. And before we start, let's see. How many people feel comfortable with breadth first search at the moment? Can we see hands? Guys, raise it. That's fine. That's cool. So like half of the class. So this means we have enough source points to spread the knowledge, right? Very cool. Very cool. So, what is breadth first search? BFS is an algorithm for traversing and searching layer-wise in tree or graph data structures. So, what do we mean by layer-wise? Now let's take a look at this animation. You can look at it from your computer. Like it first visits the one on the top, right? If we start from the root, that's the first node we are visiting. And after that we go to the second level. So in the second level we have 2, 3 and 4. And then in the third level we have 5, 6, 7, 8. And in the fourth level we have 9 and 10. And if you see, like that's the order of visit. So question, if we visited like 1, 4, 2, 3, 5, 7, 6, 8, 10, 9, would that still be like breadth first search? One, 4, 2, 3, 6, 4, 7, 8, 10, 9. What's that? It had duplicate 4, so it's not okay. Then I'm changing it. 1, 4, 3, 2, 6, 7, 8, 5, 9, 10. Yes. So basically, it doesn't matter when we hit these dots at the same level. If they are at the same level, one can come before the other or after. However, there is one thing that we know for sure. If we are doing breadth first search, the nodes that are in the higher levels are going to be visited before the nodes that are in the deeper levels. So let's say if 9 is visited before 6, then it means this is not breadth first search, because 6 is above than 9, right, in terms of level. So we can be searching all the nodes, we can be looking for a specific destination. This really depends what is our objective. But usually this is about having a graph and looking for something on it. It can be distance, it can be looking for existence of a node, or any other given criteria in the problem. And Tim, one thing that I want to remind, sometimes the problem may not look like a graph problem at the beginning. You may be given a string and looking for something in the string. But if you create a graph from that string, it may make your job a lot easier. So don't just look for a graph. Sometimes if it is given in another form, still consider. Like let's say after a while you are not making progress on the problem as is, then try to transform it into a different space. Like imagine if making it like a graph is gonna make your job easier. Because sometimes there are problems like that. You know, it's given in a different form. It's not giving you a graph. Your job is to construct the graph and then solve it with the graph traversal algorithms on top of that. And if you feel stuck in different space, then consider, can I make a graph out of this? If it is possible, this is also one thing that you should consider. Of course, there is no guarantee the problem is going to get solved with the graph traversal, right? At the same time, it may be solved. So that's why, keep it in mind. Maybe a transformation is going to be the way to get to the efficient solution. And in BFS, we are using Q. And once we go into the details of it, we will understand why Q is a very handy data structure for traversing given graph or tree with, or let's say graph, because trees are also graph, right? With breadth first search. All right. So now let's take a look at some of the real-world applications, because we are learning these algorithms. The reason is these algorithms are helping us to solve some real-world problems. Otherwise, why we were going to use them, right? If it's not making any use in real life, why are we learning them? So now let's take a look at some of the applications. So finding shortest path, right? When we go from place A to place B, it's good to know what the shortest path is so that you can get there in the shortest time. And CPU scheduling, like we have many applications running at the same time, right? The browser is running, but I'm pretty sure if we go to the task manager, we are going to see, I don't know, maybe like tens of different processes running at the same time. So they shouldn't be starving. Like they are important to keep all the system running. For that reason, CPU scheduling can make use of BFS as well. Detecting cycles in the graphs, another application. GPS navigation to find neighboring places, this is relevant with shortest path. Call center phone systems to hold people, right? So you have people waiting in the line and you don't want them to starve. Solving puzzles, like navigating in the maze. So all these problems can be seen as some real-world applications of breadth-first search. So, how does BFS work? So BFS starts working from a node. This can be any node in the graph, but in many problems, this is usually specified. So you have a start node. And then it traverses the graph layer-wise. Like we mentioned about that, by layer or by level, what we mean is the distance from the top. Like imagine your start node is always at the top. So if on this graph or on this tree, you want to start from tree, you shouldn't represent the tree like this. So the tree node has to be on top, and then 1 should be the child of tree. Does that make sense? Your start node is the node that is the top of the traverse tree. So now let's take a look at this example. We are given this graph and we are starting from 0. So we keep track of two things, guys. We have Q, and at the same time we keep track of these nodes whether they are visited or not. So that's why we have this visited as well. Because we don't want to visit the same node again and again, right? Like because BFS guarantees that we are going to discover a node with the shortest path. If you get to a node, it is guaranteed that there is no shorter path to come to that node. Because the way the algorithm works gives us this guarantee. And once we look at the details, we are going to understand why this is the case. So, we start from 0 in this example. That's where it starts from. And we place 0 into our queue. And we also mark 0 as visited. Because we start from it, right? We are already there. All the nodes that we see, they are going to be marked as visited. And at the same time, they are going to be pushed into queue as well. And after that, we look at the children of 0. Because that's how we can go other places, right? Through the edges in the graph. That's how we traverse. So, then we look at all the children of 0, and in order to do that, we first take it out from the queue. So we only keep elements in the queue when they are ready to be processed. But when they are not processed, this is important. So at the beginning, we remove it. Once we look at the implementation, we are going to see it again. But now let's imagine queue is the place when the nodes are ready to be processed. So 0 was ready, 0 was in front of the queue, we mark it as visited. And then we take the 0 out of the queue, so now we are processing 0. Because it was the first node who get into the queue and who is ready to be processed. That's why we get that one. And now what we are going to do is we are going to look at 0's children's. And we have 1, 2, and 3. And we are going to place all these nodes into the queue. Because if you remember, BFS guarantees that when we get to a node, we get there with the shortest path. So at the beginning we start from 0, right? And it's already the shortest path. We are on 0. And is there any way that I can reach to 1, 2, or 3 shorter than 1 distance? I mean, they are not my start node, right? By definition, there will be at least 1 distance. And for that reason, I push them into the queue and I mark them as visited. So this is important. I am marking them as visited when I am pushing them into the queue. Because it is guaranteed that every node is going to be discovered in BFS with the shortest path. So when I see it, I say, okay, so this guy is already processed or ready to be processed. That's why I mark it as visited. Okay, whenever we discover them, we mark them as visited. Does that make sense? Not in the processing. Like this is something that, at the beginning people might get confused. We don't wait until the node is completely processed. Whenever we discover it is guaranteed that we discover this node with the shortest path. For that reason, we mark it as visited when we are pushing it into the queue. And after that, I also see 2 with the help of this 0, 2 edge. Not because of 1, 2 edge. Okay, because I'm processing 0. I'm looking at all the children of 0. And after that, I discover 3. That's another child of 0. And again, I mark it as visited, and then I push all these guys into the queue. So, what kind of data structure queue was? It is first in, first out, right? Whoever comes in first is going to be processed first. So when I am completely done with process of 0, what am I going to do is, I'm going to proceed. And I'm going to get the top element from the queue, which is 1. And then I'm going to remove it from the queue, because I'm about to start processing. Okay, so it doesn't have the rest of it, I guess. So it just gives you the beginning of it up to this point. I think after the code, we are going to have the full execution. So, how are we going to avoid cycles? Because 0 is going to go to 1, 1 is going to go to 2, or 0 is also going to 2, right? So how am I going to make sure I'm not getting back to 0? How do we do that? Right? That's the reason we are using visited. When we discover a node, we mark it as visited this way. If a node is marked as visited, then I don't push it to the queue. I know that it was already seen before, so there is no reason to try to process it again, right? It's already in the queue. If it's not processed, it's going to be processed. Or the other cases, it has already been processed. If that is the case again, no need to reprocess it, right? So whenever I see a node that is already visited, I don't do anything about that. So, now let's continue. This was our state, right? So now I take the 1 out of the queue and I start processing it. So, which edges 1 has? It has one edge to 0 and it has another edge to 2, right? So, is 0 marked as visited? Yes. Am I going to do anything about 0 now? No, because it is already discovered, right? It's either already processed before or it's in the queue. I don't know about that. It can be either, right? All I know is it has seen before, and that's the only knowledge I need, because now I don't have to do anything. Either it is already processed or it's going to be processed because it's in the queue. So now I continue with the next one, which is 2. So is 2 visited? That is also visited, right? For that reason, again, the same. No operations for 2. So I couldn't discover any new nodes with the help of 1. And what am I going to do after that? I will continue the process, right? And go with the next node that comes from the queue, which is 2. So now 2 is going to first look for 0, let's say. We are processing the edges in the order. And 0, it is already visited, so I don't take any actions. And then I'm going to look at 1. And that's also already visited, so I'm not going to take any actions. But this time I'm going to discover a new node, which is 4. And 4 is going to be placed into the queue, and it's going to be marked as visited. Again, whenever we discover a node, we mark it as visited. Okay? So now let's make a little bit of exercise. So, instead of this, instead of marking the nodes as visited when we discover them, what if we mark them as visited when we process them? What is going to happen? Can somebody tell? Yes. Okay. Right? Because it's, let's say 4 is already in the queue, and like here 4 may be not a good example, so let's go back a bit. So in this state 0 was already processed, right? And when we discover that sorry, like here, let's go back a bit. Yes. So let's say we are marking nodes after they are processed. In that case 2 is not going to be marked as visited, right? Because we didn't process 2 yet, right? 2 is not going to be marked as visited. So when 1 discovers 2, what is going to happen? Since it's not marked as visited, we are going to place 2 into the queue again, right? So when what's going to happen is we might have multiple instances of the same node, and there is no point for that, because when the first 2 is going to be processed, we get all the data we need from 2. And when we see the second 2, right, we are just going to ignore it. And for no reason, we are going to be overpopulating our queue. That's why we want to mark the nodes as visited when we discover them. Does that make sense? So in terms of accuracy, let's continue with the other version, where we are not marking them as visited when we discover them. Would that still be accurate? Like, is it going to give us the shortest path or whatever we are looking for in the problem? Any ideas? Can we see hands? Is that? Yes. Right? Like when we see the node in the queue about to be processed, if we see that, oh, this was already processed before, and because it was going to be marked visited, right? If we check that, and if we ignore it in the second appearance, then it's going to work accurately, right? But it's going to have this inefficiency, right? And we want to do things efficiently. So that's why. And Tim, like this is exactly why I am going into these details. Because if you really understand the logic of the algorithm, then you will be able to make this type of thinking with ease. So right now, when you have this type of questions, if it feels hard, then it means there is a little bit a little bit more to learn about the logic of it. Okay? So don't be afraid of doing this type of exercises, and we are gonna get there. We are gonna get there. After doing exercises, everybody in this class has the potential to feel comfortable and give the answer you have provided by the end. If you are not there yet, don't worry about that. Because we haven't been on this track for a very long time. We had the inconsistency, that's fine. But we have the time in the cap. We have everything we need, so we are gonna get there. Now let's continue. So we were here, right? I think we had discovered 4, and then we pushed it in the queue and marked it as visited. And now we continue with the front of the queue and we get 3, and then we couldn't discover anything new, and then we are done with the process of 3, and then we get 4, so we couldn't discover anything new, and we are done. So once all the elements are finished in the queue, what happened? We are done with the process, right? So we traversed the tree, and can we tell at this point how much time did it take to get, or what is the distance from 0 to any of the nodes? Did we have enough information up to this point to calculate these? And how can we do that, yo? So what should we do to keep track of those distances?
I guess from the beginning we can't have like some kind of counter that just decides the distance, the label. And every time when we say a new node, that's the label, like the distance from the beginning. And when we go to a different label, we can increment.
Yes, and how do we know that we are going to a different level? So let's start from the beginning, right? And Tim, it is always easier to imagine these type of things with the easy cases, okay? Don't try to understand it when you are looking at the full graph. Try to understand it from the beginning. When things look hard, make it easy for yourself. Because if it looks hard, it means we are not going to get there in one step. So can I jump from here to there? I don't know. Okay, so let's make it like this. Can I jump from here to there? Definitely not. Definitely not. So if I try to jump from here to there, if I set this expectation to myself, I'm going to set my path for the failure. For that reason, if it seems not reachable, then make it easier for yourself. Then I'll be like, okay, I'm not going to reach there, but in order to reach there, I guess, how about reaching there first? Maybe it's going to make my job easier, right? Think about the simpler version. So what do we do in the first step? So when we start from 0, what is the distance? It is 0, right? Or 1, like whatever you accept. And after that, like the first nodes that you discover in the first level, what's their distance? 1, right? And let's say we are in the middle right now. And I know the distance from behind, okay? So let's say I know the distance from start to me is n. What is the distance that for the nodes that are just about to be discovered with one step? N plus 1, right? So what we can say is the nodes that we are about to discover or we are discovering, their distances, the current node's distance plus 1. I mean, we are assuming that the graph has equal edges right now. No weights or one weight edges, let's say. Are we cool with this? Great. Now let's continue. So when are we gonna stop processing? When the queue is empty, if we are looking to discover all the nodes, right? If we are searching for a destination node. When we reach that node. What do we mean by reach? When we discover or when we process?
When we discover.
When we discover, right? Yes, because when we discover a node, Tim, let's remember this. When we discover a node, we already know it's guaranteed we get there with the shortest path, right? And I know my distance, and it's just one step away from me, right? When I'm discovering it. And I know that the shortest distance it can possibly get is n plus 1. So for that reason, when we discover the node, we can finish the process. Again, like another point, right? At the beginning, we may feel like, oh, maybe it should come when we get it from the queue, when we pop it from the queue. Yes, that will still be correct, but we will be doing a little bit more process, right? If we want to be super efficient, then we can actually finish the process when we discover the node. Because we discover everything with the shortest path. That's why, when we see it for the first time, when we are about to place it to the queue, or when we are about to mark it visited, you can say, hey, I already find the shortest path to this node. And you can stop processing at that point. Cool. Any questions up to this point? Great, let's continue. Okay, like I think we have already covered this logic, so I guess we can skip this one. So now let's take a look at the code. Let's see how this is going to look like when we are implementing it. So now we have an implementation in Python, and I guess majority of the class feels comfortable, right? Is there anybody who doesn't feel comfortable with Python now? Can we see hands? So like, is it like you don't feel comfortable when you see the code, or you're not feeling comfortable to use it in the interviews? To use it in the interviews. Okay, then that's fine. In the interviews team, you can always choose whatever language seems the best fit. Like sometimes I had interviews with companies. In one I use Java, in other I use C++. Whichever feels more comfortable, and I use C as well. You know, sometimes it felt it felt easier, you know, to do things with structs rather than defining classes and stuff. So I also use C. And in the interviews with the same company, I did all these guys. Because they are not trying to measure your level of understanding in a specific language. They are really looking forward to see like what is your capacity to solve problems. Okay? Keep in mind what is their objective. So whichever tool looks handy, you can use that. Don't force yourself to use one specific language. Okay? So we have this flexibility. Don't forget about that. Alright, now let's take a look at the code. So we are given a graph and start point. I guess we are going to be traversing all the nodes. So visited, of course, using it as a set makes sense, right? Or like if you already know a number of nodes, you can get a Boolean array, and then you can mark things that way too. And we have a queue, and I guess in different languages you have different ways of creating queue. Again, it's a simple data structure, and I guess everybody uses Java, C++, or Python here in the class, right? Is there any other person who uses another language? Can we see hands? Okay, and all these languages have a queue data structure already built in. So, as long as we have nodes, because we said there is no destination, right? We will continue execution until we finish everything. As long as we have nodes in the queue, we keep going with the execution. And first we get the top element from the queue. And after that we look at its neighbors in the graph. And if we find a neighbor that is not visited yet, then we mark it as visited, and then we push it in our queue, or append it to our queue. And we continue execution like that. So in this BFS example, to keep things simple, it's just printing them level-wise, right? It doesn't calculate distance. So let's say we want to make this modification on top of that. We want to add the distances on top of that. What kind of modification we should do? Anybody wants to give it a try? Roots? Yes. So we can keep track of the distance of the current node, right? I mean, if we start doing it from the beginning, then we will have it once a node is about to be processed. And when we are pushing the newly discovered elements into the queue, we can mark their distance as current distance plus 1. Because in this graph, like, we assume all the edges are weighted with 1. Cool. Is everybody clear with this? Alright, let's continue. So now let's take a look at the complexity of time and space complexity of the algorithm. So in terms of time complexity, team, when we are trying to understand this type of time complexity things, sometimes it is easy to understand it when we look at the code. And sometimes it is easier to understand if we actually conceptually think about the algorithm. So when it comes to graph traversal algorithms, I would say it is easier to understand the complexity algorithm conceptually. So now let's think. How many times do we mark one node as visited? Once. How many times a node is inserted into queue? Once. Are we making any assumptions when we are saying once? What is the assumption? That's true. Any other assumptions about the graph? Yes. Because if there is a disconnected node, right, there is no way we are going to mark it as visited. So, if we are talking about general graphs, let's say at most once, right? And team, it's very important to be as specific as possible in computer science. And in the future, you are going to get a lot of benefit from this. Because if you see things this way, if you communicate this way, if you are not satisfied with gray areas, then you are going to be a better computer scientist. And you will be also a better data scientist, you will be a better machine learning engineer. So those are the roles I have seen. I'm pretty sure this is going to help you in other aspects of life as well. But these are the ones that you get the benefit immediately. So try to be as specific as possible. Alright, so now we understand, we are going to visit, we are going to push everything into Q and we are going to process everything at most once. That's great. So we get V complexity, right? From here. Like as V represents number of nodes in the graph. Cool. So now let's consider the edges. How many times are we processed an edge in this traversal? Once, right? We are not going to look at the same edge again, because when we are processing a node, we consider all its children. So this means considering these edges, right? And when we are looking things the back way, since the node is already visited, we are not going to process that edge, right? So we are going to process it once, and we are going to look for it once. Because in the other way, since let's say when I process the other node, or when I discover the other node, there is an edge between us, that edge is going to be processed at that time, right? And that edge is going to be looked again when it's time to process the other node. Like assuming we don't stop processing when we see the destination. And in this scenario, there is no destination, right? So it's going to be looked once more. But if we look at the asymptotic time complexity, is it going to change anything? No. And do we do anything else? Like maybe some initializations, right? And are they going to take more time than V or E? So now let's take a look at that too, right? To understand the space complexity. So what do we use additionally to what we are given, which is graph and star? We take the visited set, right? How many elements can we have at most in this visited set? V, right? And this depends on the implementation behind, but let's say what is the default implementation of Python in implementation of set in Python? Is it hash set, tree set? Anybody knows? It's hash set. If it is hash set, what is the complexity of inserting an element or looking up whether it exists there? Constant time, right? For that reason, it's not going to be like V log V or something, right? It's going to be V. Because pushing and looking up, they are all taking a one time, constant time. Cool. And let's say if it was tree set, then what would have been the complexity for that operations? Log V, right? Look up and insert, it would be log V. Cool. And team, it's important to know this type of details about your favorite programming language. Especially if it is Python, because Python has tons of useful functions which has the underlying complexity. And if you don't know about that, it may be very easy to do your time-space complexity analysis in a wrong way. Alrighty. So, in terms of space, yeah, we have the visited. What else do we have? We have the queue as well, right? And how much of a space the queue has? Louder. It's also V, right? OV. Yes. So in total our space complexity also comes down to OV. Cool. So, now let's take a look at this sample question. We are given a 2D integer matrix consisting of only ones and zeros. And our objective is to find the shortest path length in a maze from a given source to a given destination that only passes from once. And if it is only passes from once, it is guaranteed that the source, the start and the destination, they are both ones, right? Okay. And there are also 4 types of valid moves. So we can only use the main directions. We can go up, down, right or left. And when we are going up, what do we do? Johannes, do we do this? Okay, so now when we take a look at this example, we see that there is one shortest path, right? So the blue ones actually represent the shortest path. And now, let's see how we can work on this given problem with the help of BFS. So since it's asking about shortest path, when you see shortest path, usually BFS is very handy. Whether the graph is consisting of edges weighted one or with different weighted edges, still BFS is a very handy algorithm there. So we are going to see that modification too. When the edges are weighted, how can we deal with this situation? But for now, let's focus on this simple problem. So we are given a maze here, right? So how can we represent this as a graph? Anybody wants to help with that? Yes, Kalam.
All adjacent cells consisting of all ones. There's an element
All adjacent nodes, cells,
that are all ones.
uh-huh.
There's an
That's great. So basically, we are creating nodes from the cells which has 1 in it, right? So those are the nodes, because we don't really care about the nodes that have 0 in them, right? And we put an edge between two nodes when they are adjacent to each other, meaning they are reachable with one of these valid nodes, right? Okay. Is everybody clear with this transformation? How did we create the graph from this given maze? If there is somebody who is not comfortable, please raise your hand. Okay, looks like everybody is comfortable with this transformation. That's cool. So, we can actually imagine this maze as an undirected graph, right? And as Kalab suggested, we can create nodes for the ones and put edges between the ones that are reachable to each other with the valid moves. And after that, we can also keep track of the steps taken, right? So that's kind of the distance. We already talked about this part. So let's say we start from 0, 0. And how many steps we have taken so far? 0. And then we discovered that 0, 1 is actually reachable by 0, 0. And what is going to be the steps taken for that one? It is discovered with the help of 0, 0. And 0, 0's distance was 0. So it's going to be 0, 1's distance then. 1. And then we continue the process. And we are processing 0, 1 right now. And we discover two nodes here. 0, 2 and 1, 1. And since 0, 1's distance was 1, what is going to be the distance for 0, 2 and 1, 1, which are discovered at this level? 2, right? 1 plus 1. And this way, I think 0, 2 is discovering 1, 2 and 0, 3. And since 0, 2's current distance was 2, when it is being processed, when we discover 1, 2 and 0, 3, we are going to mark their distance as 3, which is 2, that was the current distance of 0, 2 plus 1. And now, when we look at a complete solution here, so there are a few things that can be handy. So that's why let's do a little bit of analysis on this code. So, at the beginning, we initialize the 2D visited and directions arrays, it says. And since we are representing the cells in the maze as nodes, that's why our visited array here is 2-dimensional. So no need to try to transform it into 1 dimension, right? I mean, as long as you have a way to distinguish nodes from each other, you can use as many levels, as many dimensions as possible. And team, this is something that I highly recommend getting comfortable with. Because if you really understand the logic of DFS in 1 dimension, it's going to be very easy to apply it to 2 dimensions, 3 dimensions, even 4, 5, 6 dimensions that is hard to imagine in mind, right? But you will be able to implement it. So I can give you 6-dimensional space, define the valid moves. As long as these are given, right? You should be able to implement it. So instead of having like 2 levels, you're going to have like 6 levels. And the valid moves are going to be different. But if they are given, you can do it in the higher level of dimensions as well. Nothing is complicated there. Alright, so now since we are given 2-dimensional maze, and we are representing the nodes with their x and y coordinates, that's why we initialize our visited array as 2-dimensional array. Because if given x and y, we can go to a node. And that's why we are doing the same for the visited array. And team, we are given that the main directions are possible, right? For the moves. And for that reason, creating a directions array is very handy. And the direction array is actually focusing on the relative distance between the current cell and its neighbors. So now let's take a look. Let's say my coordinates are x and y. If I add 0 to x and 1 to y, where am I going to get to? Can somebody tell? 1 step down. Or like let's say x, y plus 1, right? It was 0, yeah, it's the same thing, yes. X, y plus 1. And if we actually add 0 minus 1 to xy, we get to x, y minus 1. So that's another neighbor. And if we add minus 1, 0 to xy, we get x minus 1, y. And likewise, if we add 1, 0 to xy, we get x plus 1, y. And if you look at these guys, these are the valid moves that were defined in the problem. So that's why this destination array, sorry, this directions array actually make your job easier. Otherwise, you are going to be writing all these relative coordinate differences by hand, and this is going to increase the risk of making a bug. So if you do it through with this array, like it's easier to see that, like 0, 1, 0, 1, 1, 0, minus 1, minus 1, 0, 1, 0. It's easier to see if you make a typo here than adding it into the code down. Alright, so now we continue. And Tim, is there anything that you would not recommend in this implementation? So once you see the implementation, once we look at the parameters of the function, anything that you would that we can improve? Yes. Visiting it when we first get it as a neighbor. I mean, that's already done that way, right? Before it's added to the queue, it's marked as visited, no? What is it? If it says... Okay, okay. I see. It's a minor improvement on what it is, right? Yes. So any other, let's say, more basic suggestions to improve the code quality yesterday? Oh, okay. So that's a practical improvement, but let's not go into that, guys. Okay, so I'll try to take, yes. Variable naming, right? I mean, it's the obvious one, like IJ, this is not a good variable name for parameters, guys. Those are dummy variable names, right? So there is a reason why we are using it that way, because of this convenience. When I look at the code at Google, at Palantir, at Liftoff, I can easily understand those are dummy variables because they are used in the loops, right? But if we use it as a function variable here, it's gonna get me confused because I'm so used to see them as dummy variables, you know? And if they have different meanings here, like coordinates, it's not gonna make your job better. You know, it just confuses me right now. So I wouldn't use this variable naming, and I highly recommend leaving them for loops. Okay, cool. So now back to the topic. Now let's take a look. So we define the directions array, and then we define our queue, and we are starting from our start point, and then we mark it as visited, right? So that's important. When we are pushing something into the queue, we mark it as visited, right? And the start node is not any exception to this. And after that, we start with the execution. So the minimum distance at the beginning is initialized as maximum number, right? And let's not forget that, because we may, if we forget to initialize it, and if the default value is 0, what is going to happen? We are not going to be able to update it, right? And we are not going to calculate the right result. So this is something that we can make a mistake, you know? Even sometimes I do that. So that's why it is important to initialize variables, guys. And better to just take a second to think about it. If you are trying to calculate minimum of something, then initialize it very high. If you are looking to get maximum of something, initialize it very low, so that updates can take place. Alright, and then we start our execution. So we get the top element. And if we already find the destination, we just put the distance that we found so far, and then we return. So, what kind of execution is this, guys? This is not what we have described, right? Because it actually returns when it is not discovered, but when it is being processed. So it is doing a little bit more process than needed. So it's not the most efficient, but still a correct solution. But now we are able to understand this type of trade-off, right? So this is when you actually understand the logic of the algorithm. Then you are like, oh, okay, so when we do it, it's gonna make this. When we do that, it's gonna make that. So when we get to this level, then the modifications are gonna be easy, because in the interview, they are not gonna ask, hey, you are given a graph which has edges once, and it's undirected graph, and just print them in the level order. They are not gonna ask textbook description of BFS. Then everybody would pass the interview, right? So that's not what they are looking for. They want to see you actually get the logic and you are able to do the modifications, because that's the real problem solving ability. Alright, so then we continue, and then we check the directions. So if the move is valid, and is valid function checks whether we are still in the maze and it is 1 and it's not visited. So Tim, this is a very nice way of implementing this. Like, look at the look at the inside of the isValid function. Like indeed, in order to make a move valid, we have three conditions. First, we gotta be in the maze, right? Like if you are not checking this, you may try to reach to part of the array that is not yours, part of the memory that is not yours, and then that you can get like segmentation fault in C++ and different types of errors in different languages. And maybe in some languages, if it automatically allocates the memory for you, it's even worse. You are gonna make mistakes and you're not gonna even realize that. So, better to follow for that, okay? So we should know where is ours. So that's why it is important to check whether we are still in the maze, right? If we are on the edge of the maze, like let's say I get to here, I always go to the right neighbor, and I'm here. So do I have any other right neighbors? No, right? I am done. So we have to check that. That's why there is this check on top, which is making sure that we are still in the maze. So that's one check. What is the second check? We said we can only move around once, right? Those are the ones that we consider as nodes. So that's why it is also checking whether the node that we are considering has one in it or not. And it has to be one so that we can process. And lastly, what was the other check? If it was visited before, is there a point pushing it again to the queue? No. That's why we have to check it is also visited. And Tim, is there any order of importance here? Like we said three things, right? Checking whether this is in the maze or not, checking that it has one, and checking that it is visited or not. Is the order important here? Yes. And what is the importance?
You have to check the maze first
Before the other two, right? Because if it is not a valid cell, then if we try to reach whether it's one or whether it's visited, then we are going to have an error, right? So that's why we have to first check it's valid, it's in the maze. Makes sense. Very cool. And as you see with the helper function, your main logic is going to be simple. And in different questions, the conditions can be different, guys. Maybe in a different problem, they are going to say the move is only valid if your node's number is greater than your neighbor's number. Let's say it's going to put different numbers in it. And it's going to say you can only go to nodes that are smaller than yours. You know, well, they can have different types of modifications. But if you look at the problem this way, and if you have different levels of abstractions, it's going to make your job a lot easier. So that's why we try to play it with the best way, right? And I highly recommend doing this abstraction and outsourcing this part of the work to a helper function. You don't have to name it as isValid. You can choose your name. But instead of trying to do this whole thing in one line, which is making the code dirty, harder to understand, and it's increasing the risk of having a bug. I highly recommend having this level of abstraction and using a helper function there. And after that, what do? So we just check all the nodes that are available in different directions. And then we check whether the move is valid, and then we do the update. So here, is there any other improvement for the readability of the code? So let's just focus on this part, the loop part. And we don't have the line numbers, but 4D in directions, from 4D in directions to Q.append lines. So any improvement suggestions there? A little louder, but... Yes. Yes, that's a great idea, because we just keep repeating I plus D0, J plus D1 3 times there, right? And again, we are increasing the risk of making a bug here. So right now, it's not written with a bug, so it's correct, but why do we have to do it this way, right? We can actually create two new variables, maybe nx, ny, or ni, nj with the language of this. I wouldn't suggest ing. But just to represent, this is the new node that we are discovering, right? Have it into two variables and just refer to them with the variables. And don't think of this as, oh, now I'm getting extra memory here. Guys, readability is more important. And you are not changing asymptotic complexity. And getting one variable, come on, we can get like millions of them, right? It's cheap. And when it's cheap and it is increasing the readability, do increase the readability. It's more important. Cool. And after that, like, we just check whether this move is valid. If the move is valid, then we mark it as visitor and then we push it to the queue. And actually, I'm checking where is the distance update is being done. While appending to the Q, okay, so we are inserting with this plus 1, so Q keeps track of the distances, right? So, yeah, that makes sense. Okay. And let's say we wanted to make the more efficient implementation, then what else were we gonna add inside of this part, inside of this if?
Check for the destination.
Right? So the check that was being done before, it should have been done here, right? Then it's gonna be more efficient. Very cool. So, team, do we have any questions? Or is everything clear? Everything is crystal clear? That's perfect. That's why I really like working with you guys. Because you are smart, you get it very quickly. Okay, so the next question. Up to this point, we were interested in calculating the distance, right? What if the question also asks, okay, so I want the shortest path from you. How am I gonna get there? What can we do? So basically, here we calculate the shortest path's distance from source to the destination, right? What if the question was also asking, okay, print the shortest path as well? Very cool. So every time we discover a new node, if we actually keep track of that, the new node is discovered by the parent node, right? If we do it for all the nodes, whenever we get to the destination node, the destination node knows where it came from, right? And then the other node also knows where it came from. And this way, by going back, I can go back to the start node, right? And that way I can actually reproduce the shortest path that I went over to calculate the distance. Does that make sense? So is everybody clear with this part? This part is very important, guys. And if it's not clear, please raise your hand. Yes. Now let's take a look, and then it's going to be easier to understand. Thank you, Henok. And Senya, you are included too. If it's not clear to you, you should also raise your hand. Is it clear to you? Okay, then come back. Cool. Alright, team, so now let's try to understand the idea here. It's better to look at it from your screen, and then I will refer to the cells with the coordinates. So, team, the suggestion Kalab made was, when we are discovering a new node, let's keep track of where I came to this new node from. Because when I'm discovering a new node, I know that it is discovered by the currently processed node, right? So basically what I keep track of is, for the newly discovered node, I say it is discovered because of the currently processed node. So let's say we started from 0, 0, right? And 0, 0 discovers 0, 1. Right? In the process, first it discovers 0, 1 because it has 1 and it's next to it. It's one of the main directions. So that's why it's going to be discovered by 0, 0. And when we discover 0, 1, we say that 0, 1 is discovered by 0, 0. So you can do this by having an additional array. And like let's say parent, because that's also actually keeping track of your parent, right? At the end of the BFS traversal, we are generating a tree. And we can say that that's our parent. And we keep track of our parent node. So 0, 1 says I came from 0, 0. So what kind of array is this gonna be? So how many dimensions is this gonna have to keep track of the parents? What's that? 1? Why 1?
Restoring the parent of 1.
But how do we refer to these nodes?
What's two-dimensional array, right?
Yes. So first of all, it's two-dimensional array that we refer to things, right? And we also keep track of 2 coordinates. So it's gonna be like, let's say the maze dimensions are n by n. It's gonna be an array of n and 2. And the reason it has the 2 in the end, because for each parent we want to keep track of x and y, right? So we need to know its both coordinates so that we can distinguish it. So is this part clear to everybody? Let's say we are discovering this guy from here, right? How do I represent this node? I do represent this node with 2 dimensions, right? So let's say the parent array, it's gonna have x and y dimensions. And again, team, instead of trying to think it for all, make it easy for yourself. Try to understand it from the basics, from the simplest pieces. So here, we are trying to understand it from this guy, okay? I can reach to this guy by x and y, right? And what is the parent for this guy? It is 0, 0, right? And in order to keep 0, 0, what do I need? I need 2 dimensions, right? So you can get like tuple of these, or if we are representing with an array, it's going to be like this. So is everybody clear with this part? And if we keep track of the parent all the time, whenever I discover a new node, if I mark its parent's coordinates to this array or like another place that you choose, then we will be able to reproduce the path, right? Because what is going to happen is, everybody is going to know who is their parent. Like if we represent this with an array, it will be different, but I think this analogy right now should be understandable, right? So basically we are able to see each of these edges, right? Like the green arrows, let's say. Is this part clear?
Yes, but the child can have 2 parents, right?
The child cannot have 2 parents. The child has 1 parent, but the parent has 2 coordinates.
Yeah, not in the shortest path, but the possibilities of the parents. One child can have 2 parents.
I wouldn't say so, because right now we describe parent-child relationship as whoever discovers the node for the first time becomes its parent. So when I'm being processed, like I am taken out of the queue and I'm being processed, and then I look at my children, right? So if they are not visited, then I become their parent. And when I become their parent, no one else can be their parents. Is this part clear? What if we are asked to find the longest path? Indeed, BFS is not going to help you. And longest path problem is an NP complete problem, so there is even a song for that. You guys can search for it. Find the longest path. I will send it to the group. It's a fun song. I like it. Yeah, finding longest path, guys, yes, it sounds weird, right? Finding the shortest path is a lot easier than finding the longest path. And sometimes in life things are like that, you know? The simple solutions can take you to the best results. Yeah. Cool. Back to the topic, yes. We can also save them as a pair, yes. So when we are saving a parent, when we say we save it as a pair, it means the parent has 2 dimensions, right? And in order to distinguish the parent, that's why we need 2 variables. It can be a tuple, it can be a pair, right? It can be 2-dimensional array to represent these 2 coordinates. But the idea is basically distinguishing parent from other nodes. Does that make sense? Just because we define the nodes with 2-dimensional array here, like we refer to them with x and y coordinates, that's why our parent array is like this. So if it was given in a normal graph, if we refer to the nodes with 1 dimension, then the parent array is going to be also 1-dimensional. Does that make sense? So let's not get confused here. The reason the parent array is like this is because we are distinguishing nodes with 2 dimensions. That's why in the first place we have these 2. Because this guy gives me a node in the maze, right? And after that, since each node is represented with 2 coordinates, that's why I also need this dimension. Because I want to keep track of the parent, and I cannot distinguish parent with only 1 dimension. Because if with 1 dimension, I can either keep track of x or y, not both. Are we clear now? Cool. Any other questions, team? So now we understand why if we keep track of parents, indeed, we will be keeping track of these arrows, right? So now, let's also take a look at the part where we are going to extract the shortest path. So, now let's look at the additional code that we introduced into the existing one. First off, we initialize the parent, right? And I think in this code it is, it is not referring to it with this 2-dimensional array, but as we said, this is equal to having a pair or tuple. Everybody is clear with this part, right? Okay, in the code I think it is referred as a tuple, right? In Python it's called as tuple. Okay, so the first thing is obviously initializing this parent array. And the second thing is, when we find our destination, or the second thing is, when we are doing the discovery, whenever we are about to mark it as visited and push it to the queue, we also mark its parent. And as you see, when we are going to ID0JD1, which is the new discovered node, we mark its parent as INJ, because I came from IMJ. This is where I got discovered. Or this is what I'm about to discover if you look at IJ's perspective. And that's why I mark it. And in the end, when I find my destination, I also extract the shortest path. So now let's take a look at the extraction code. I think that's the last piece that we didn't cover. So at the beginning, the path is empty, right? And then I start curating it. So as long as I don't see the value that I put for distinguishing the start node. So it says here -1, -1, right? So whenever something is not visited, it has -1, -1. And there is one difference in this, not all the nodes have parents, right? Not all the nodes that are visited have parents. So which node doesn't have a parent? The start node, right? So that's actually where the execution is going to start for this code. So now I continue in the while loop as long as I have a parent. And I start from the which node? From the destination, right? Or the last node. Yes. Because I can extract it from starting from the end, guys. Look at the arrow like arrow directions. It's not from the beginning to end, right? It's connected the other way around. So everybody knows who they come from, not who they went to, right? This is very important. So that's why when we create the path at the beginning, it's gonna be reversed, right? Because we keep track of the directions in the opposite direction. So that's why we start from the last node, from the destination node, and then we get its parent, and then we append them to the list or whatever data structure you choose. And after that, we reverse it. So that's important. But once you have it one way, right, you can do the execution from other way. So if you find something in the reverse way, you already find it. So you can just do the change the processing way. So now are we clear with this part? How are we going to construct the shortest path? Or the path that we find with the help of BFS? Okay. So now we see why it is important to understand the logic of the algorithms, right? Because if we get the logic, team, like now, for example, it's been a very long time I didn't implement BFS. But if I'm supposed to implement BFS, I have 100% confidence that for the basics I'm going to implement it. Because I know the logic. And the logic is a lot easier to save in your mind. Let's say I don't do BFS practice for 3 months. If I get the logic still, I can retrieve it. But if I try to understand the code, like the code is very complicated, man. If I don't take a look at this for 3 months, I'm going to forget about that. So that's why, focus on the logic, guys. That's what matters. You can write the code. You already know how to write the code. But if you get the logic, then you're good. So, now let's see if instead of the 4 main directions, if we are considering also diagonal moves, what is it going to change? Just the direction array, right? Because of our implementation, if you weren't using the direction array, your code size was going to be doubled, right? So that's another reason why we use the direction array. Because if you did this logical abstraction, it doesn't matter how stupid the moves are defined. You know, it can be like, okay, so you are going to jump there. Sometimes you have questions on chessboard, right? And it asks, okay, so you travel with this, let's say, queen. Or you travel with, I want to say horse, what is it called in English? Knight, yes. In Turkish we call it horse, that's why. Okay, yeah, when you want to travel with knight, like it's a weird type of a move, right? It's L-shaped. But again, the idea is thinking about the relative difference. So if you define it that way, all you gotta change is the direction array. And then your code is gonna be very generic. Like the code that you write for, what's it called? Knight is gonna be similar to what you write for queen or is it rock. Yeah. Because only the neighbors are changing, right? So the direction array is gonna be changing. That's it. How about 3D space? Again, it's the same, right? So also you are going to add the dimension to distinguish the code. Instead of having the visited array with 2 dimension, you are going to have it 3-dimensional. At the same time, you are going to update your directions array too, right? And you can actually do the same thing in 3-dimensional space as well. Okay, so I think we have already covered this. You mean for the direction or?
No, actually, 3D BFS.
3D BFS. Okay, I don't think we have the code, but we can talk about the changes in this code, for example. And like first, the visit is gonna be x, y, and you're gonna add one more dimension for z. And second, like for the parameters, instead of ij, x, y, you're gonna get ij, k, and it hurts me every time I say this. And x, y, z. And as we go down, the directionary is gonna be three-dimensional. Instead of having 4 elements, I think it's gonna have 8 elements, right? In the three-dimensional one. I mean, if we are considering only the main elements. So the directions array is gonna look like this. So each variable again gets 0 and 1, and you try all the combinations. And when we are marking things that we already mentioned, the visit array is going to have 3 dimensions, and the parent array is going to look like this: x, y, z, 3. And again x, y, z to distinguish the nodes, and 3 because the parent node is going to be distinguished by 3 dimensions. That's why we are going to need this much of a space. And yeah, in the implementation, like the change is actually very similar. So everybody is clear with this part? Because team, like this type of modifications can come, you know, and it actually confuses many people. So who have a shallow level of understanding of the algorithm, they are going to get confused and they are going to fail. And that's exactly what they want to separate with these interviews. They want to see people who actually get the logic. Yes, very good. So now let's try to see it with another example. So if let's say we are given a graph here. Let's say this is our graph. And let's say we want to discover 5 from 1. So we want to discover the shortest path to 5 from 1. So we know that we start from here and we know that its shortest path distance is 0, right? Is there any objections for this? So we know that this guy is already reached with the shortest distance, right? So now, when we are trying to do this type of things, guys, it's always better to start from the basics. Try to understand it from the beginning. And then it's going to be easier to construct and generalize our understanding for larger situations. So, when we are looking at 2 and 3, so these are our immediate neighbors, right? If a node is not the start node, is it ever possible to get there with a shorter distance than 1? I mean, if all the edge weights are 1, right, it's impossible. So we know that a node's distance to the source node, if the node we are talking about a node that is different than the source node, is going to be at least 1, right? And for these nodes, our BFS says their distance is 1. So can we say that they are also shortest path? Like 1 is the shortest path for them, right? So then I know that these nodes also reach with the shortest path, right? So now I have a larger group of nodes which are reached with the shortest path with the help of this BFS algorithm. So now let's take it one more step. So now let's consider the nodes that are discovered next from this group. Like for example, 4 is going to be discovered. And is it ever possible that a node that is not in distance 1 to the start node to have a short path that is smaller than 2? No, right? I mean, if it's not immediate edge, if it doesn't have a direct edge with the start node, then the shortest path, the minimum value of the shortest path is going to be 2, right? And for 4, what does it say? The BFS says its shortest path is 2, right? And in the second step, can I say that this is also taken into the nodes that belong to the shortest path? Can I safely say that? Right? Because it's not an immediate neighbor, right? And for that reason, the shortest, it can find this, it can have the lowest value it can get is 2. So that's why I can say that 4 is also discovered with the shortest path. So now let's take a look at 5. So what does BFS tells for the discovery of 5? It says that the distance is going to be 2 with the help of 3, right? And again, for a node, is it ever possible to be discovered with a path that is shorter than 2 if it's not an immediate neighbor of the start node? No. For that reason, if I get there with 2, I know that it's also shortest path, right? So this way I get here. And let's say my destination was 6. So now I'm going to use the logic with one more level. And this time I'm going to say, is it ever possible to get to a node that is not an immediate neighbor plus that's not an immediate neighbor of the immediate neighbors. Is it ever possible to get to this node with a path that is shorter than 3? No. And the BFS tells we get to this node with path 3, right? So again, we know that this is also discovered with the shortest path. So now if you play it to distance n, and we know that it's discovered by the shortest path, right? And for its immediate neighbors, we know that if we get there after reaching this parent node with n distance, n plus 1 is the shortest possible distance that you can get for the shortest path. So this is how we can say that the BFS is actually guaranteeing us the shortest path. So I didn't give you a formal proof, and you guys can ask Burak first to teach him shortest path, sorry, BFS, and then ask him to give you the mathematical formal proof for that. But I guess, like, what was this method called, Erdem?
Induction.
Proof by induction, right? Yes. So this is how we actually guarantee that BFS gives us the shortest path. Alright, so now we have one more modification. So now we are not given a graph with equally weighted edges. So we are given a graph which has edges that have different weights or different costs, whatever you want to call. So now in these circumstances, with applying the logic of BFS, how can we find the shortest path? Any recommendations? Any ideas? Yes, Issa. Or sorry, we see another hand. Abdi. Yep. So when all the edges all the edge weights were equal, the idea of the BFS was still start processing from the node that we know for sure it has the shortest distance, right? So that guarantees that we do things level by level, right? And when the graph has edges, actually it's not about the level. It's about the distance to the source node. So that's why we modify our logic. Instead of using a regular queue, we use a priority queue or heap. And again, the idea is, if a node is reached by shortest path, and if it is discovering a node with a distance, then we know that that node, when it is discovered, is having the shortest path through this guy, through that edge. But there is no guarantee that that is the shortest path for that guy. Because the step I am taking right now, it can be very large, right? And there can be another node which has more distance to the start node, and it can give a better solution. So now let me try to describe this scenario here. So let's say from 1 to 2 we have edge 1, edge weight 1. And from 2 to 3 we have edge weight 100. And from 1 to 4 we have edge weight 2. And here we have edge weight 2. So when we do the execution here, we start from 1, right? And then we discover 2 with distance 1. And then we discover 4 with distance 2. If I insert these two guys into a min heap, which one is going to come to my hand first? 2 with distance 1, right? And when I get 2 with distance 1, then what do? I continue my execution, right? This is the node that has the shortest distance to the source node. That's why I start the execution from this guy. But team, there is one very big difference here. Like now, when I discover a node, I don't guarantee that I get to this node with the shortest path. Because when the edge weights are different, the discovery does not guarantee the shortest path. Like this is a very major difference between weighted graph and unweighted graph. Or a graph with equal weights. Are we clear about this part? Because in the weighted graph, we can only guarantee the shortest path when this node is about to be processed. When that came out of the heap. Because the min heap keeps the minimum value at the top, right? And if I'm always processing the minimum value, when a node is taken out of the queue, I can guarantee that I get to that node with the shortest path. Does that make sense? It's a very major difference, and that might be the reason why actually it is implemented that way in the first place. Because it doesn't want to give you any difference between weighted graph versus unweighted graph for the check of the reaching to the destination node. Because now the previous implementation is actually forced. We cannot do the pruning of, oh, whenever I discover it, I can report the result. Because This 3 is going to be first discovered with the help of 2. And then it's going to insert to our queue 3101. Right? So this guy is gone when it's processed. So I mark this as visited 2. And this is going to be the situation I have. And another major difference, team. I am not marking nodes as visited when I discover them. Because the same node can actually be found through a shortest path with the help of another node which had initial distance to the source node higher than the current node that is being processed. Look at here. 2 is processed earlier than 4, right? And 2's distance to 3 is 100. Sorry, 2's edge length to 3 is 100. And the total distance I discovered with the help of 2 from beginning node to, let's say, 3 is our destination node, is 101. And when I discover this, it is not guaranteed that it's the shortest path, guys. Because the last step might be a very large one, as in this case. Okay? So that's why I can guarantee the shortest path when I am taking the node out of the queue, when I'm about to process it. So that's a very major difference between weighted graph, shortest weighted graph BFS versus unweighted graph BFS. Are we clear with this difference? If you are not clear, please raise your hand. Yes? Say it again.
For instance, we inserted 3 first, right, to the heap.
We inserted 3 first.
Through the distance of
3 101 first, yes.
Yeah, right. So by the time we have to take out 3, maybe we can prove that the other 3, the path to 3, are already inserted.
Yes. We are going to get there. That's going to come, yes. So basically we guarantee that when we take the node out of the queue, that node is reached with the shortest distance. Because any other distance we can create from after this point is going to be longer than that. Like right now, I am done with 2, 1, right? Is it ever possible to create a distance that is shorter than 1 with other elements in the queue? No. And now soon after I'm going to get the 4 out of the queue. So now this one is, let's say I'm done with the process of 2 now, right? And then 4 is taken out of the queue. And now, is it ever possible to create a distance with the elements in this heap that is less than 2? No. For that reason, we know that it has the shortest path. So now, let's continue. So, I am processing 4 right now. What is the current distance of 4? It is 2, right? And when I discover this edge, what kind of distance, total distance I see to 3? 4. So at this point, if I insert 3, 4 to the priority queue or min heap, what's going to happen? This is going to go top, right? And with this way, actually we are able to discover the shortest path to destination node 3. If we didn't do that, if we actually mark it as visited or deported as soon as we discover a node, we were going to be making a mistake. Because the last step can be a very big one. The weights are not equal anymore. For that reason, I cannot say that, oh, whenever I discover a node, I know that it's the shortest path. When the edge lengths are equal, we can do that. But when the edges are weighted, the last step can be large. For that reason, I cannot guarantee the shortest path until I know for sure every element in the queue has a greater or equal distance to what I discovered so far. And this can only happen when I'm taking the node from the queue. Does that make sense? Are we all clear with this part? Very cool. Guys, if you also get this part, then it means you are good to go for BFS in the interviews. Alright, so now let's continue with the execution. This guy comes to the top. And then I get 3, 4, and then I see that there is no newly discovered nodes, right? Because this is also marked as visited. And again, this time I am marking things as visited, not when I am pushing them into the queue, when I am taking them out of the queue. So, now let's look at the implementation here. So, we initialize a heap, we initialize the visit set. And at the beginning, we get the element on the top of the heap. And again, we are starting the heap with the 0 distance and with the start node, right? Node represents start node here. Again, not a good variable naming. Because start node is also a node, destination node is also a node, right? And calling it node is just confusing us. So that's why it's very important to have good variable naming, guys. You can confuse yourself too, and many people do that. So if you are like, oh, I'm good at coding, but I am bad at variable naming, then I would ask you to rethink. Because if you are good at coding, you cannot be bad at naming, you know? Okay, cool. Or let's say you can be good, but you cannot be great. In order to be great in coding, you gotta be great at variable naming. Cool. Because otherwise it makes things complicated, right? Like when I see this in the at down, like when it says node is inserted to heap, I'm like, I mean, node is a node, so what's going on? Then I'm like, okay, so this is the start node, right? So that's why if it's a start node, better to name it as start node. Or start rather than node. This is not a good naming, confusing. And you're gonna confuse yourself if you do bad naming. So do good naming. Alright, so next. We inserted the first element, and then as long as we have elements in the heap, we keep going. And then we pop the top element from the heap. And this time we have the cost or distance and the name of the variable. Sorry, and the node, the current node. And if the current node is equal to destination, then I can report the cost. And again, this is different than the other one, right? In the other one, we were able to move this part into the if. When we were discovering the node, we were able to stop the execution. But in the weighted graph, this is not the case. So that's why I can only stop the execution whenever the destination element comes out of the heap. Because I know that in the further levels of execution, there is no way I can generate a distance that is lower than what is already discovered for this node. So we are all clear with this part, right? Now let's continue with the execution here. So when I take the node out of the heap, I mark it as visited. That's another major difference with the unweighted BFS. In the unweighted BFS, I was able to mark them as visited whenever I discover the node, because I know that when I discover it, it is discovered with the shortest path. Because the last step cannot be any larger than other steps. All the steps are equally weighted. For that reason here, for the weighted BFS, I have to do it here. And again, guys, I am not suggesting to memorizing it like this. I'm not suggesting, hey, just to be clear, always mark it after you get it from the queue. No, what I'm suggesting is understand the logic and do the most efficient way. Because if you really get the logic, it's not going to be difficult. You are going to think, when am I guaranteeing that this node is discovered with the shortest distance? I am guaranteeing that when I take it out of the queue, if it's weighted graph, right? So that's why, focus on the logic. Get the logic, the rest is going to be easy. Then, we mark it as visited, and after that, we look at the neighbors, and when we find a neighbor that is not visited, I push it to the heap. So, are we clear with this part? Like the logic, all the steps why we are taking in the places that we are taking them? Okay, very cool. Thank you very much, team. And again, it's a big pleasure to work with you guys because you guys are very smart. What's that?
And a smarter line.
I think you guys are smart. Alright, so now let's take a look at the time complexity here. So team, here again, one thing that is different with this. In the normal BFS, in unweighted graph, is it ever possible for a node to enter into our queue multiple times? No. How about this version? Yes, right? We have seen the example of it here. 3101 was in our queue, and then 34 is also inserted, like let's say prior to queue or heap, right? So one node can be inserted multiple times. So what is the theoretical bound? How many times can a node be inserted the most? As much as we have edges to it. And how many edges can we have? N, right? Or V. Yes. Like E is the total number of edges. The question was how many times one node can be inserted to the queue the most theoretically? N times, or N minus V or V minus 1 times, but you get the point, right? Like possibly every node can rediscover it, and every time it can be discovered with a shorter distance, right? And even if, let's say, it's not with a shorter distance, we will try to push it if it's not processed yet. So for that reason, theoretically, the same node can enter V times. But you're right, the V comes because the number of maximum possible edges is V to NO, that's why. And in total, how many elements can we have in our queue at most? Theoretically again. Any ideas? V square. V square because of what? That's right, that's a good one. And what is V square? At the same time, it's an upper bound for something. Number of edges, right? So can we also say that like number of edges times at most? Because every edge can push something into the queue, right? So E and V squared, they are both correct. And if you want to be more specific, we can say E. since we are using both variables in our asymptotic time complexity analysis. Okay, so now if we try to look at the total time complexity here. So we said we can push elements E times, right? And V might be larger than E, that's why it's represented as V plus E, to get the maximum of them. And how many elements can we have in this heap? Up to V plus E, right? So as a result, what's the cost of inserting an element to heap or getting it from the heap? Log n if we have n elements in it, right? If we have V plus E elements in it, it's going to be V plus E, log V plus E. So as a result, our total time complexity is going to come to V plus E times log V plus E. Are we all clear with this? And again, team, like you see that, right? When we actually try to understand the logic and go step by step, everything is clear. And even the time complexity analysis can be done with the help of the logic. So that's why if we focus on the logic for all the algorithms we are covering, things are going to be easy, guys. So let's continue doing that. Very cool. And for the space complexity, again, we are getting the heap and visited. So we say that in the heap we can have at most V plus E elements. That's why the space complexity is going to be V plus E as well. And yeah, I think since we have already covered this, no need to go over it. Okay, and I mean, since there is an exercise, let's do it, right? It's fun. Okay, team. What is going to be printed? There is this print function. Now let's take a look at the code. I want a logical sentence. What is being printed? Let everybody think about it for a while, for a minute, and then we'll get it. All right, team, back to here. Enoch, now.
The previous statement, the current node we are the minimum cost to get to reach that.
Yes, and if we basically continue printing things, what is it gonna print by the end? Like everything can.
All the nodes with the minimum cost to reach.
Yes, so basically it's gonna print them with the short span, right?
But we didn't check if they already visited.
Yes, so that's a very good discovery. Actually, Kidus was mentioning that too. So, team, actually there is one bug in this code. I mean, eventually it's gonna find the right result, but it's gonna do more processing, let's say, and still it can be called as a bug. And what is it? So, Isaac.
Just checking of the
Yes, where should we do that? Yes, so basically, whenever we pop an element from the queue, we should check whether it was already visited before or not. If it was already visited, is there a point of reprocessing it? When are we marking nodes as visited here? When they came out of the queue, right? And if something already came out of the queue before, can it have a larger distance than that we currently have? No, because it was processed before, right? And we always increase, like the minimum number we get from the heap, always increase, the costs are always going in the increasing way, right? So for that reason, there is no way when the node is popped for the second time, it's gonna have better results than the first time. So that's why whenever we pop the element from the queue, we can check whether it was already visited before. I mean, visited means processed, right? If it was already processed or visited before, there is no point to do it again. So what is the implication here? Is it making our code wrong, or let's say the returned result wrong? Leaving it as is it making it wrong? Danny, what do you think? Without making any update, right? It will just overpopulate the heap, and that's not going to affect the minimum cost that we calculated, right? But well, it's not guaranteed if the neighbors didn't pop it. Because we mark them as visited when we pop, right? Because some of them can be reinserted. Yes, so it's gonna do some unnecessary calculation basically. No need for that, right? So that's why when we take something out of the queue, we should also check whether it was already visited, because visited means processed. Are we clear with this? Improvement. Cool. Yes, because it's returning before. Very clear. Yes, for the sake of complete accuracy, right? Thank you. So f cos 6 is not going to be written actually.
Yeah, exactly.
Yep. Okay, so the second exercise. What if we move the print into the if? Then what's going to be the output here? First logical explanation. Again, take a look, think, and then have a discussion with your neighbors. All neighbors are valid. With distance 1 or 2. Tim, did we produce the output? Do we need more time? Who needs more time to produce the output? Can we see hands? Are we all done with producing the output? That's perfect. Okay, so now let's take a look at the output here. So any objections to this? Can we see hands? Any objections to the printed output? Yes, Abdi. C8 should be in the list, right? And if other people have no objections, Hoca, come on. Did you guys really do the tracing of the code?
C8 in 14, there should be like 9, E9.
There should be also E9. Because of what? I don't think so. E9 may not be necessary because because E is going to be processed before C. So C is going to be, right, A is going to be marked as visited. Yeah. E, sorry. Okay, team, do we understand why C9 is going to be printed? Sorry, C8, right? Abdi, could you please come here? Please, this honor is yours. Come. Because you are the only person who has seen that. Who didn't go with the flow. Because the flow was in the wrong direction. Great catch, yes. Okay, so now, team, like there is a bug that we mentioned, right? Kidus and Isaac pointed. So we do not mark the nodes as visited when we pop them out, or actually we don't check whether they were already visited. So we continue reprocessing them. But it's actually independent from that. Even if we were doing that, C8 was going to be printed. Because we do not guarantee that we are not going to insert anything with a higher cost than distance into the heap. The same node can enter multiple times, right? This is actually what's happening here. I think here is the graph. So you can actually drop it on top of it. It's fun. Right? Oh, let's use another color. Thank you. Jim, the focus is important. We see that. And Abdi, congratulations for staying focused. Alright, here we go. Can see the code from there? Oh, you choose the one.
So, first, like, at first,
Team, attention to the board. Yes. If you don't see it, you can check the graph from there, but that's the same.
A is in the heap, so like we pop first A, then A child A neighbors will be printed in their values. For example, for this one, B first will be printed. The cost will be 2. So after that, B will be pushed into heap. Then the heap will be 2. After that, we pop B. There is only one node in the heap, so we pop B in the we push B's child and we check we make B visited after popping from the heap, then push B neighbors to the heap. It will be 4D and 6C. At that point, we print D4 and C6. After that, the first node will be for D because it's minimum. It's 4 and 6, so the minimum will be its mini heap, so it will be at the top. Then we pop for D. Then when we pop it, we make the node visited. So this child will be pushed into E, into heap. So 5E will be in the heap. Then we print E 5. Then we pop from this, and the minimum value is 5 compared to each other. It will be E at the top. So we pop E and we push its children, its neighbor, and it will be C and F. So C is not popped, so it's not visited. So the children, the neighbors will be the heap will be I think C 8C and 6F. So between
Also 6C, right?
yeah, 6C.
Yes.
We print C8 and F6. So after that we pop it's equal, so it gives priority for the longest stage element in the heap. So the C will be popped, but the children are also the neighbors are visited. So we don't have to create anything. And we pop 6. It should be finished.
Yep. Thank you very much. And that's a great catch, Abdi. Congrats. Alright team, so as we see, since we are writing things when they are discovered, there is no guarantee that a node is not going to be discovered with a higher value after. Because if it's not visited, we don't know. That's why we should push it to the heap, right? That's why we said, hey, there is a kind of like a inefficiency here, like multiple elements or the same element is going to appear multiple times, right? And in order to prevent this, let's say you are writing this implementation and it's going to be implemented billions of times every day. Then what you can do is you can actually do cross-reference. From your heap, you can have a list and then you can have a, let's say, here you have an array and then you are pointing all the elements in this heap. So when 6C is already in the heap, like let's say here, this is A, this is B, this is C. So C is going to be pointing to this guy. And when you are considering whether you should insert 6C in this or not, you can actually check whether, 8C in this or not. You can actually check whether the value that is already found is greater or not. So you can keep track of these shortest distances somewhere, right? And whenever you see something larger, you can say, hey, there is a shorter already in the heap. So no need to insert this. So that's how you can prevent the larger values to be inserted to here. That's nice. But still, it doesn't guarantee that if you keep track of the cross-reference, you can actually guarantee that every node is going to appear in the heap once. But if you just keep track of the numbers, let's say you don't have this reference to here, and you just write 6 here, then you will guarantee that whenever you see something larger, it's not going to be inserted. But when you see something smaller, let's say we discover C bit 4, it's going to be inserted, right? And if you don't have this edge, if you don't know where this guy is in the heap, you're not going to be able to find it, right? So you can make this one 4, and you can insert 4C into the heap. So this way, you make sure the numbers are always going down, right? But you don't guarantee that the heap is not going to have multiple appearance of the same node. Does that make sense? So now we see the trade-off there, yeah? Yes? A little louder, Ishaq, I don't know.
We're also adding integer to string, so what would actually be printing is concatenate only string.
Okay, so it's going to be writing them like string, you say. I see your point.
It's going to create an
Yeah, we have to put parentheses there. You're right.
No, you can't put that with integers. You have a conversion.
It's either the-
Oh, there is no automatic conversion because in Java it does that, but in Python you have to do it. Okay, okay, okay. Thank you, thank you.
So nobody got the right.
Still, I give the credit to Abdi. All right, cool. So when to use BFS, team? Like if you are making any search on the graph, you can use BFS. Like there is no reason to use DFS or BFS if you are just doing the search. You know, so that's why any kind of graph search is needed. If that's the generic problem, then you can use BFS there. That's first. If you are looking for shortest possible distance, minimum cost, minimum distance, these type of keywords, actually very good pointers for BFS. You know, because it helps us to calculate the shortest distance, minimum cost, this type of things, right? So look for these type of things. And it can also be used for cycle detection or exploring graph, because for exploring we said, right, DFS and BFS both are available. BFS is also available. Or like some maze, grid questions. These type of questions usually definitely consider. It may be handy. And some sample questions. We have 10 of them, I guess, here. So some of them I think you already solved before. That's fine, you can skip them if you feel comfortable. If not, you may also revisit them because, yes, I have seen pretty much all these problems, but now I don't remember the solutions, you know. And if you are in a similar situation, it might be nice to re-implement them. Or if you want to work on different problems, feel free to do that too. And let's finish with the quote of the day. And that comes from Suha's favorite sportsman. Suha actually put together these slides. And the quote is, I know where I am going and I know the truth, and I don't have to be what you want me to be. I am free to be what I want. Yes, we always have the free will, guys. Thank you very much, everyone. And I think that's it for today.